Hello. So, in the last class we have started discussion on radial basis function neural network, and we have seen that a radial basis function neural network consists of three layers. One is of course the input layer, and one of the three layers is the output layer, and in between the input layer and output layer we have a hidden layer. So, unlike in case of multi-layer perceptron, where we can have one or more hidden layers, in case of the radial basis function network, we have only one hidden layer, and every neuron in the hidden layer computes a radial basis function. So, when I have the neurons in the hidden layer, for every neuron which computes a radial basis function, radial basis functional value for an input feature vector, every radial basis function has got two parameters. One is called the receptor and other one which defines the spread of the radial basis function. So, the architecture that we have is something like this. We have one input layer. So, the input layer contains a number of neurons, and the number of neurons in the input layer is same as the dimensionality of the feature vector. So, if the feature vectors are of dimension d, I will have d number of nodes in the input layer. So, there will be d number of nodes when the dimensionality of the feature vector is d. In the hidden layer, I will have a number of nodes and suppose the number of nodes in the hidden layer is say capital M. So, as we discussed in our previous class that the purpose of the hidden layer nodes is to project the d dimensional feature vector into a higher dimensional feature vector. So, as I have m number of nodes in the middle layer, so obviously this m, the number of nodes in the hidden layer is greater than the dimensionality of the feature vector, which is d. And as we said that every node in the hidden layer computes a radial basis function. Like this. And at the output layer, which are basically the classifying neurons, I have the number of neurons or the number of nodes, which is the same as the number of classes that we have. So, if I have c number of classes, then at the output layer I will have c number of neurons. So, there we have c number of neurons, where c is the number of class in which the patterns are to be classified. Then every node in the input layer is connected, is feeding input to every node in the hidden layer, and output of the hidden layer, every node output from the hidden layer is connected to every node in the output layer. So, I have the connections which is something like this. So, these are the connections from the input layer nodes to the hidden layer nodes, and because the purpose of this connection is simply to forward the input feature vector to the nodes in the hidden layer, we can assume that weight of each of these connection is equal to 1. And that is a difference with the connections from the hidden layer to the output layer nodes, because in every output layer node computes a linear combination of the outputs of the hidden layer node. So, the connection from the output layer node to the connection from the hidden layer nodes to the output layer nodes is something like this. Sorry. Where we can say that every ith node in the hidden layer is connected to the jth node in the output layer through a connection weight which is equal to W I j. So, because of this, every node in the output layer computes a linear combination of the outputs of the hidden layer, and based on this, the value of this linear combination, the output layer nodes decides to which class the input vector should be classified. Now, what can be done is, these output layer nodes can also impose a nonlinear function to ensure that if a particular input feature vector belongs to class omega j, in that case only the output of the jth node will be equal to 1 and output of all other output layer nodes will be equal to 0. Similarly, if a feature vector, input feature vector belongs to say class 1, then only the output of the first node in the output layer will be equal to 1 and outputs of all other nodes in the output layer will be equal to 0. So, as we discussed in the previous class that such a radial basis function network, an RBF network, incorporates two types of learning. One is, we have to learn that for every node in the hidden layer, because every node in the hidden layer represents a radial basis function, what should be the receptor of that radial basis function and what should be the spread of that radial basis function. So, if the radial basis function is a Gaussian function, that is, if it is something like this, say phi of x is equal to say e to the power minus x minus t square of this upon 2 sigma square, where t is the receptor and sigma, which is the variance, it decides that what is the spread of the radial basis function. So, for every ith radial basis function phi I x, t I is the receptor and sigma I is the spread. So, I have to know that what is the receptor for every radial basis function and what is the spread of every radial basis function. So, this is one level of learning. And the second level of learning is, once through these radial basis functions a d-dimensional feature vector is projected onto an m-dimensional feature vector. So, basically what we are doing is, we are increasing the dimensionality of the feature vector. And as we have indicated in our last class, that the purpose of increasing dimensionality is that if the feature vectors are linearly non-separable in the d-dimensional space, when we cast them into a higher dimensional space, then the possibility that they will be linearly separable in a higher dimensional space increases, and this possibility increases with the value of m. So, as we increase the dimensionality more and more, the possibility of linear separability of the feature vectors also increases. So, the feature vectors in the d dimensional space which are not linearly separable, when I cast them into an m dimensional space where m is greater than d, it is more likely that those feature vectors will be linearly separable in an m dimensional space. And once the feature vectors are linearly separable in the m dimensional space, then the linear combination of the outputs of these hidden layers is likely to give me the class belongingness. And that linear combination is decided by the weight vectors, by the connection weights from the hidden layer nodes to the output layer nodes. So, we also have to learn that what should be the connection weight w I j from say ith node in the hidden layer to the jth node in the output layer. So, this is the second level of learning. So, in the first level of learning, for every radial basis function, we try to learn what is the receptor and what is the spread of the radial basis function. And for in the second level, we try to learn what is the connection weight from the input layer from the hidden layer nodes to the output layer nodes. And as we have discussed in the previous class, that the usual way, a common method of learning the radial basis function is, if you are given a set of feature vectors for the training purpose and suppose value of m is equal to 3. Okay. So, what we do is we partition or we cluster this set of feature vectors into 3 number of clusters. So, if we have m number of nodes in the hidden layer and I have say n number of feature vectors, which are given for training purpose, and I have m number of nodes in the hidden layer, obviously, in this case n has to be greater than m. Otherwise, clustering n number of feature vectors into m number of clusters does not make any sense. So, I have to have more number of feature vectors than the number of clusters that I have to form. So, I cluster this n number of feature vectors into m number of clusters, and I can assume that centroid or mean of every cluster represent the corresponding receptor. Okay. So, if I take ith cluster represents the receptor of the ith radial basis function. So, the situation is something like this. If I have a set of feature vectors, so these are the feature vectors belonging to different classes. Typically, what I do is I cluster these feature vectors into 3 different clusters. Every cluster center now represents a receptor. So, this is one receptor, this is one receptor, this is one receptor. So, this is the receptor T 1, this is the receptor T 2 and this is receptor T 3. So, the first operation that we have to perform is the clustering of the feature vectors, and this clustering operations we will discuss in details in future lectures. Okay. Now, once I have these different receptors, to find out what should be the spread of a particular radial basis function, what we do is, for say ith receptor, I find out p number of nearest neighbors or p number of nearest receptors, and for this p number of nearest receptors, I compute what is the mean distance or root mean squared distance. So, there are different possibilities. I can take any value, I can choose any value out of these p number of distance values. So, what I do is the way I compute sigma I for the ith cluster for the ith radial basis function is I have T I, which is the receptor for the ith radial basis function, and then I take p number of nearest receptors which are nearest to T I. So, suppose one such receptor is T k. So, what I do is I compute T I minus T k square, take summation of this for k is equal to 1 to p, as I have p number of receptors, 1 upon p of this and square root of this. So, this defines the spread of the ith radial basis function. So, for every ith radial basis function I have T I and I have sigma I, and once these two are known, then my radial basis function phi I of x is simply e to the power minus x minus T I square upon 2 sigma I square. Okay. Now, let us see that by using this concept, whether I can make a linear classifier using the radial basis function concept for the XOR problem. And XOR is a very common problem, which is used for illustrating such operations. So, as we have said earlier, if I take an XOR function, I have a 2-dimensional feature vector, binary feature vector having components x 1 and x 2. Suppose this represents 0, this is x 1 equal to 1, here I have x 2 is equal to 0 and here I have x 2 is equal to 1. The value of the XOR function when it is 0 0 is equal to 0, 0 1 the value is 1, 1 0 the value is 1 and 1 1 again the value is equal to 0. So, you find that here I have 2-dimensional binary feature vectors, and what I do is this 2-dimensional feature vector I want to cast into a 4-dimensional space by using 4 radial basis functions. So, I have the radial basis functions phi 1, phi 2, phi 3 and phi 4. For phi 1, I choose T 1 is equal to say 0 0. That is the receptor of the radial basis function phi 1. Similarly, for phi 2, I can choose T 2, which is a 0 1. That is the receptor of the radial basis function phi 2. Similarly, the receptors of other radial basis functions I can choose as T 3 is equal to 1 0, and for this I choose T 4 is equal to 1 1. So, these are the 4 receptors for the 4 radial basis functions. Next, I have to choose the spread sigma 1 for the first radial basis function, I have to choose sigma 2 for the second radial basis function, sigma 3 for the third radial basis function and sigma 4 for the fourth radial basis function. Now, for this, for every receptor, I have to find out p number of nearest receptors, and suppose I choose that value of p is equal to 2. Now, here you find that for every receptor, there are 3 neighbors. 2 of the neighbors are at a distance or at distances of 1, and one of the neighbors is at a distance of 1.4, that is square root of 2. So, that is easily verifiable from here. I have a receptor over here which is T1, T2 is at a distance 1, T3 is at a distance 1, but T4 is at a distance of square root of 2 which is 1.4 or 1.414. So, when I take P is equal to 2, I have to take two nearest neighbors, both of them are at distance 1 and root mean square distance of these two distances will also be equal to 1. So, I have spread sigma 1 is equal to 1, I have spread sigma 2 also equal to 1, I have spread sigma 3 also equal to 1 and I have spread sigma 4 that is also equal to 1. So, I get phi 1 x which is of the form e to the power minus x minus t 1 square of this upon 2 sigma 1 square and sigma 1 being equal to 1, this will be equal to 2. Okay. Similarly, for phi 2 x, I will have e to the power minus x minus t 2 square of this upon 2, phi 3 x will be e to the power minus x minus t 3 upon 2 and phi 4 x So, if I compute these values for each of the feature vectors, taking 0 0 as one of the feature vector, 0 1 as another feature vector, 1 0 as another feature vector and 1 1 as another feature vector, the functional values will be something like this. So, I put that in the form of a table. Here I have input feature vectors, inputs are 0 0, 0 1, 1 0 and 1 1. And I have the RBF functions phi 1, phi 2, phi 3 and phi 4. So, when you input the feature vector 0 0 to phi 1, you find that your x is equal to t 1. So, this exponent is equal to 0, which means that phi 1 x will be equal to 1. So, this phi 1 x over here, this will be 1.0. Similarly, for phi 2, my x is 0 0, where t 2 is 0 1. Okay. So, if I compute this phi 2 x, you will find that this phi 2 x will be equal to 0.6. Similarly, I will just put the values over here, phi 3 x will also be 0.6 and phi 4 x will be 0.4. When the input vector is 0 1, phi 1 x will be 0.6, phi 2 x will be 1.0, phi 3 x will be 0.4, phi 4 x will be 0.6. For 1 0, this is 0.6, this is 0.4, this is 1.0, this is 0.6 again. And for the input feature vector 1 1, I have phi 1 is equal to 0.4, phi 2 x will be 0.6, phi 3 x will be 0.6 and phi 4 x that will be 1.0. Okay. So, you find that given a two dimensional feature vector 0 0, this has been cast into a 4 dimensional feature vector, where the components of this 4 dimensional feature vector are 1.0, 0.6, 0.6 and 0.4. Similarly, 0 1, this is a 2-dimensional input feature vector which has been cast into a 4-dimensional feature vector, the components being 0.6, 1.0, 0.4 and 0.6. So, every input feature vector where the input feature vector is a 2-dimensional feature vector, every 2-dimensional input feature vector is converted to a 4-dimensional feature vector by using 4 radial basis functions. Now, if I take the linear combination of this, and for linear combination for phi 1, if I give an weight of, say, I give the weight for phi 1, I give an weight of -1, for phi 2 I give an weight of +1, for phi 3 I give an weight of +1, for phi 4 I give an weight of -1. Okay. So, the function that I will finally compute at the output at a node in the output layer will be phi 2 plus phi 3 minus phi 1 minus phi 4. And if I compute this, let us see what are the values that I get. So, here I will write sum of W I times phi I, where I varies from 1 to 4. So, here it will be 0.6 plus 0.6 is 1.2 minus 1.4, this will be minus 0.2. Similarly, here it will be 1.4 minus 1.2, so it will be plus 0.2. Here again it will be 1.4 minus 1.2, so this is plus 0.2, and here it will be 1.2 minus 1.4, so this is minus 0.2. And if I take a decision that if the value is more than 0, the output will be 1, if it is less than 0, the output will be 0, then the final output that we have is, here I write output, this will be 0, this will be 1, this will be 1 and this will be 0. So, which is nothing but the x of function output. So, over here the architecture of the radial basis function that we have used is, we had 2 input layer nodes where x 1 is fed to one node and x 2 is fed to another node. I had 4 nodes in the hidden layer, which computes the radial basis function, and I had one node in the output layer, which I can say that it is finding out it is a nonlinear operator or a threshold operator. The connections are like this. Where each of this connection has a connection weight is equal to 1. And over here these connections are, as you can see over here, phi 1 to output layer node has a connection weight of -1, phi 2 to output layer node has a connection weight of +1, phi 3 to output layer node again has a connection weight of +1, phi 4 to output layer node has connection weight of -1. So, here the connection weights are -1, +1, +1, -1, and this output actually gives me the XOR function. Okay. So, this example clearly shows that by casting the 2-dimensional feature vectors into a 4-dimensional feature vector, I can implement the XOR function using a linear network or a single layer perceptron, because this part is nothing but a single layer perceptron. Okay. So, now let us theoretically try to find out an expression for the training of the output layer, or how do I find out this connection weights. So, in general, I have a network something like this. I have a set of input layers, set of input layer nodes. I have a set of hidden layer nodes, and I have a set of output layer nodes. The feature vector is fed to the input layer nodes. So, here I feed x, which are fed to the hidden layer nodes, through connection weights, which are 1, and outputs of these hidden layer nodes, these are my radial basis functions. Outputs of the hidden layer nodes are connected to the output layer nodes. So, like this, and I take the output from every output layer node. So, if my input feature vector x belongs to say ith class, then output of the ith output layer node will have a high value, likely to be 1, and outputs of all other output layer nodes will have a low value, likely to be 0. And I assume that the ith node in the input layer is connected to the jth node of the output layer through a connection weight, say W I j. So, given this, if I say the output of the jth layer node is O j, I will have O j is equal to sum of W I j times phi I x for an input vector x, and this summation I have to compute over all nodes in the hidden layer. So, here I will have this summation has to be computed over I is equal to 1 to m, as I have m number of nodes in the hidden layer. And naturally, over here, if this feature vector x, so I will write if x belongs to class omega j, then I have to have sum of W I j times phi I x, I is equal to 1 to m. This has to be equal, this must be greater than 0. I will put this as plus 1. And if x does not belong to omega j, that indicates that sum of W I j into phi I x, I varying from 1 to capital M, that must be equal to 0, or I can also put it as minus 1. So, let us assume that if x belongs to class omega j, W I j times phi I x, that has to be equal to plus 1, and if x does not belong to omega j, this has to be 0, and that is what have to be the output from the jth node in the output layer. Now, taking this, now I can go for training of the output layer. That means, I have to find out what should be the values of this wij. Now, if I compute only the connection weights, if I right now consider only the connection weights which are connected to the jth node in the output layer, then for every vector x k, suppose I have capital N number of vectors. So, I have vectors x k for k varying from 1 to capital N. I have capital N number of input vectors which are given for training purpose or for learning, as we are using supervised learning. Then phi I of x k, for simplicity I will write this as phi I k. Now, by using this, I can as I said that sum of phi I x k into w I j k. So, my condition is, if you remember this one, so sum of w I j into phi I k for I varying from 1 to m, this has to be equal to plus 1 if x k belongs to class omega j, if x k belongs to omega j, and this has to be 0 if x k does not belong to omega j. So, this is the output that I expect. So, for x k, I have, for every x k, I have such a kind of linear equation that this summation will be either plus 1 or 0. And all those capital N number of equations, now I can write in the form of a matrix. So, in the matrix form, this can be written as, let me write the matrix equation, that phi 1 1, which means phi 1 x 1, okay, phi 2 1, that is phi 2 of x 1, phi 3 1, phi m 1, this means phi m of x 1, similarly phi 1 2, which means phi 1 of x 2, phi 2 2, phi 3 2 up to phi m 2, and as I have capital M number of samples for training. So, I will have phi 1 n, phi 2 n, phi 3 n up to phi m n, which indicates phi m of x n into w 1 j, w 2 j up to w m j. So, you find that what it computes, w 1 j times phi 1 1 plus w 2 j times phi 2 1, continue like this, w m j times phi m 1. That is, for the first input vector x 1, whatever is the output of individual middle layer nodes or hidden layer nodes, this equation simply makes a linear combination of outputs of the hidden layer nodes for than input for the input feature vector 1 or x 1. Okay. So, this has to be equal to, again I put the output in the form of vector b 1 j, b 2 j up to b n j, where every b I j will be equal to 1 if the corresponding x I belongs to class omega j, and that will be equal to 0 if the corresponding x I does not belong to class omega j. So, every b I j will assume a binary value either 0 or 1. So, this b I j will be equal to 1 if x I, the corresponding input vector x I belongs to class omega j, the jth class, or it will be equal to 0 if x I does not belong to omega j. So, this is the kind of situation that I have, and this whole expression, this matrix equation, I can write in a short form, that is phi w j is equal to b j, where this phi is this matrix, w j is this weight vector which are connected to the output layer node j, and b j is the output of the jth node in the output layer, which is represented in the form of vector like this for different input vectors. Okay. So, if the network is properly trained, that is all the w I j has got the trained value, then this equation should be satisfied. But what we are trying to do is, we are trying to train the network, that means, we are trying to set the weights w j. So, we cannot expect that this equation will be satisfied initially. So, if this equation is not, if this equality is not satisfied, then what I can do is, I can define an error E, which is nothing but phi w j minus b j. And now, training involve adaptation of this weight w j, so that this error can be minimized. So, in order to do that, as we have done earlier for mean square error optimization, for mean square error technique for classifier learning or classifier training, I can also define here a function, a criteria function j of w j, which is given by phi w j minus b j norm of this, and then I take the gradient with respect to w j. So, grad of j w j, which will be simply 2 phi transpose into phi w j minus b j. And by equating this to 0, what we get is w j is equal to phi transpose phi inverse of this into phi transpose b j. And as we have seen earlier, this phi transpose phi inverse, phi transpose phi inverse into phi transpose, this is what is called pseudo inverse, and that is represented as phi plus. So, we have w j by this pseudo inverse technique, we have this w j is equal to phi pseudo inverse into b j, okay, where b j is defined beforehand. every component of Bj will be either 1 or 0. It will be equal to 1 if the corresponding feature vector, input feature vector, belongs to class omega j, and the component will be equal to 0 if the corresponding input feature vector does not belong to class omega j. So, I have this vector Bj. Phi actually indicates that what should be the output of the hidden layer nodes for every feature vector. So, from that I compute what is my matrix phi. So, once I have this matrix phi and I have this Bj, I can compute what will be the connection weights for different nodes in the hidden layer to the jth output layer node. And this, if I do for every output layer node, I can compute what is the connection weight for from different outputs of the hidden layer nodes to different output layer nodes. And that is what completes my training of the RBF neural network, and the RBF neural network will be ready for classification. Now, if you compare this RBF neural network with your against say multi-layer perceptron, you will find that the training of the RBF neural network is faster than the training in multi-layer perceptron, because in case of multi-layer perceptron, the training is done by backpropagation algorithm, which takes large number of iterations. Okay. So, the training of the RBF neural network will be faster than training of the multi-layer perceptron. The second advantage is that I can easily interpret what is the meaning or what is the function of every node in the hidden layer, okay, which is difficult in case of multi-layer perceptron. I cannot easily interpret the role of different nodes in the hidden layer in case of multi-layer perceptron. And not only that, I also cannot easily decide that what should be the number of hidden layers and what should be the number of nodes in every hidden layer. So, those are the difficulties in case of multi-layer perceptron, which is not there in case of RBF network. However, RBF network has a disadvantage that though the training is faster, but you find that the classification takes more time in case of RBF network than in case of MLP, because in case of RBF network, every node in the hidden layer has to compute the radial basis functional value for the input feature vector, which is time consuming. So, the classification in case of RBF network takes more time than the classification time in case of multi-layer perceptron. Okay, so, with this we come to a conclusion on the new radial basis function neural network. Now, over here I will just briefly discuss about another kind of classifier, which is called a support vector machine. So, I will briefly discuss support vector machine. So, support vector machine is another type of linear classifier. So, if you remember what we discussed in case of a linear classifier, that given a 2-class problem, we have said that I can define a discriminating function, say g of x, which is of the form say w transpose x plus b, okay. And we have said in case of linear discriminator that if this g of x or w transpose x plus b, this is greater than 0, that indicates say feature vector x belongs to class omega 1, and if this is less than 0, then feature vector x belongs to class omega 2. So, here you find that for classification purpose, the actual value of g x is not really very important, But what is important is what is the sign of g x. If the sign is positive, I infer that x belongs to class omega 1. If the sign is negative, I infer that x belongs to class omega 2. Right. So, over here with every x, if I or if with every x I indicate a number say y I, where y I can be either plus 1 or minus 1. In that case, this y I times w transpose x I plus b, it will always be greater than 0 if the sample x I is properly classified, which is quite obvious, because if I say that y I equal to plus 1 for a sample x I which belongs to class omega 1, and for a sample which belongs to class omega 1, this w transpose x I plus b is greater than 0, y I is also positive. So, y I times this will obviously be greater than 0. If x I belongs to class omega 2, then w transpose x I plus b will be less than 0, and for that I have set y I equal to minus 1. So, minus 1 times w transpose x I plus b will obviously be greater than 0. And this is a concept that actually we have used when we have discussed about the perceptron criteria, okay, or designing the linear classifier. That is, for every feature vector belonging to class omega 2, we have negated the feature vector before we tried to design the classifier. So, that for every feature vector, irrespective of whether the feature vector belongs to class omega 1 or the feature vector belongs to class omega 2, my discriminant function value will always be positive if the feature vector is correctly classified. So, that is true if the feature vector belongs to class omega 1, or even if the feature vector belongs to class omega 2, because for the feature vectors belonging to a class omega 2, before trying to design the classifier, we have negated this feature vector. So, we will discuss about this support vector machine in more details in our next class. Thank you.